So in this talk, we'll switch gears a bit and talk about some fundamental issues in quantum electrodynamics from the perspective of engineering scale structures. So this talk is very much in the spirit of Alexandre's talk, the opening talk, and we'll touch on some issues in Angel Rubio's talk as well. But what we have here, so I've put up the sort of structures that Alexandre put up. What we have here is superconducting atoms embedded in metallodielectric structures instead of atoms. So it's very much in that same spirit. So this is a bit of a different composition of audience than I typically talk about this topic. So I've taken some care, including some additional discussion of outstanding challenges in the field as I see it. It's so this is sort of a personal list of challenges. So there are by now two generations of students and postdocs who have worked on these topics, and a few of the key publications are listed here as well for those who are interested. All right, so here is an overview. I will introduce the by now well-established formalism of circuit quantum electrodynamics, which uses a slightly different quantization technique than one we typically use for atomic QED systems. It turns out that the slight difference is an important one, and I will be sort of underlining that in the second part. So in part two, before part two, I will discuss some of the challenges in modeling large-scale engineered quantum systems. I will try to be as concrete as possible here within our current understanding. Next, in part two, I will introduce and discuss a specific formulation of circuit quantum electrodynamics that shows considerable promise to address some of these challenges. In fact, this theory was constructed with these primary challenges in the field in mind. We are not quite there yet, but what we have at the moment is what I refer to here as HLQED, that is specifically designed for transmission line-based circuit quantum electrodynamic systems, and I will introduce what I mean by that. If time permits, I will also touch on recent progress in extending this formulation to 3+1 dimensional superconducting systems that we refer to as DEC QED. It's a formulation of QED that is based on discrete differential forms. Turns out to be that is important at a fundamental level. And this work, part of the work is really in its beginning stages and is a more substantial program, taking a renewed look at fundamental problems in quantum electrodynamics, in particular the electromagnetic stability of charged matter. So finally, towards the very end, I will touch on model order reduction techniques built on top of these formulations. Here, time permitting, I will only touch on a few basic observations arising from recent work towards the very end of my talk. But this turns out to be, model order reduction turns out to be really an important ingredient that one needs to have. So stylistically, the first part of my talk will be really a high-level discussion. But in the second part, I will pick a prototypical problem in circuit quantum electrodynamics, and we'll get down into technical details. And some of the sort of techniques and challenges and so on that I will be talking about There are really many common threads with other quantum gauge theories, in particular quantum chromodynamics. And I will touch on these as we go on. Okay. So the motivation here is the accurate and effective modeling of large-scale quantum hardware for quantum computing and simulation. So I'm showing here on the left an early example from Google that features 9 qubits. Nowadays, we have devices that contain 50 plus superconducting qubits. But this early example is nice because you can clearly discern the basic architecture of these devices. And the bigger sort of chips are just sort of scaled up versions and improvements on top of this architecture. So, of course, for those who are not familiar with these kinds of superconducting circuits, it's not clear what this really is, physically speaking. But you can think of these gray areas really as metals. So it is mostly metal. And because it's at low enough temperatures, around tenths of millikelvin, it's superconducting. And these blue lines here, they are transmission lines, essentially trenches opened up in the metal here. So generally speaking, these kinds of systems, they come with repeated units. You have these in red. I identify the qubits, which you cannot really see because they are nanoscopic. In blue, you see that each superconducting qubit has an attached readout resonator. And all these readout resonators are coupled to a feed line on top here, where all the light, all the radiation is collected for reading out outside the chip. Yeah, and on top, specifically for this system, you have also what's called the couplers, which allow you to change the qubit-qubit coupling, or the interaction between two qubits, as is expressed by this term, in a way that you can manipulate simply by threading magnetic field through these loops. Yeah, so it's highly controllable, highly adjustable system that we have. I'm showing, so today, on the right, I'm showing a piece of quantum code. So today, these devices are accessible through cloud interface, and you can write a piece of code to carry out a certain algorithm you desire. An algorithm is really an experiment here. And there are really lower level interfaces which are publicly, at least accessible by researchers for carrying out serious experiments. A computation, which is essentially a known sequence of gates generally expressed in a so-called circuit here, as you see, for 3 qubits here. Is really the repetition of a sequence of gates on an identically prepared set of qubits. And you do that 1,000 times. You run this sort of sequence 1,000 times, thousands times. And the end result, the information that is used to sort of implement a function or do some computation is based on the probability of occurrence of each bit string of up and down states, or zeros and ones for each of the 3 qubits in this example here. This really suggests that quantum computing is really different from classical computing as we know it, because it's intrinsically probabilistic computing. But for this talk, what I want to emphasize is that computing is really all evolution of a multi-qubit system that you see here under the action of microwave and RF drives in the couplers, and subsequently the extraction of the system state through a procedure called readout. Yeah. In that respect, modeling of these systems really require the description of the dynamics of this multi-component system away from the ground state and for a system under measurement. So let me start by defining what I mean by quantum electrodynamic modeling of quantum hardware. We want to start out with an accurate quantum field theory of superconducting charged matter in this metal and electromagnetic fields. From there derive an effective quantum model for the relevant degrees of freedom. I mean, if one could construct such a computational tool, this would be of tremendous use to design of these systems. Now, by relevant degrees of freedom, I mean you are really interested in the dynamics of your qubits. So you're not interested in what is happening here in some corner of the device, though it is part of the Hilbert space, right? Specifically, we want the final model here to be describing the Hamiltonian and dissipation rates of relevant degrees of freedom. And in that respect, this final deliverable is an effective quantum model. And its most important characteristic is that it is an open one. Yeah. Now, if you dig deeper here, what is an accurate ab initio field theory that you want to start out with does not really have a well-reasoned definition, or at least one that I know at the moment and mathematically can formulate at the moment. Should one start out with electrons in this metal or the condensate, right? Once the electrons condense here. So for what I want to discuss here, we want to rather focus on the process of model order reduction. We will not worry about the starting point so much. So for what I'm going to discuss here, our starting point will be the macroscopic order parameter equations of the condensate coupled to the electromagnetic field, all second quantized. So as I promised, I want to sort of go over some outstanding challenges in the field. These are really not fully settled. It's a number of really interesting problems. So challenge one is, in modeling quantum information processors, first of all, you're not interested in the ground state or near ground state or quantities that are accessible by linear response. Ground state and low excitation substate is not of interest from the point of view of an information processor. In that respect, the required quantities that you want to compute are substantially different from those that you encounter in electronic structure calculations or correlated electronic materials that we have heard in the last 2 days. The additional maybe point that I want to make here is that information gained from the readout perspective is really information lost from the processor perspective. Yeah. So computation really requires the understanding of a quantum system dissipating into measurement channels. So you can't think of computation as divorced from dissipation and noise associated with it. That's fundamental fact. All the issues we are dealing with in quantum computing today is really because of this very fundamental issue. So therefore, all that is to say is that dissipation is the flip side of the coin and for doing computation with quantum systems, and has to be very precisely captured. Challenge two, so QED is a gauge theory, yeah, and gauge constraints and the associated spectral theory, the normal modes that you want to use of QED, is formulated in the standard sort of approach in infinite space-time volume. Yeah, we do not notice it, but only this fact allows a tremendous simplification in implementing gauge constraints. This is perhaps the key reason why in quantum electrodynamics, quantization is done in the momentum basis for the fields, because it's easy then that you can analytically express the gauge constraints. When one is confronted with QED of a complex material system, every bit of real estate becomes critical. And one ideally would desire to do a computation in a finite volume. So can quantum electrodynamics be formulated in an exact way, even in principle, within a finite volume? That's an issue I will try to address in today's talk. Challenge 3, in recent years, we have seen new engineered superconducting systems that take a renewed look at QED using what is referred to as high impedance materials. And you're seeing here a structure like that. There's a lot of detail here, but what it is that you have this line containing thousands of Josephson junction elements coupled to each other, that is then read out through this capacitive coupling. No, there's a qubit here, an atom. So this is really an, atomic is an atom coupled to a cavity that is coupled to the to external world for reading it out. Yeah. And you can think of these lossless materials providing a very strong, effective fine structure constant. Yeah. So these materials offer the opportunity to take a peek into how the world would look like if light and matter coupled in a way that cannot be described perturbatively. Therefore, there's also a need to develop calculational methodologies for QED that are not perturbative in nature. So the final challenge I want to take up is a very fundamental one, but also a very applied one: radiative corrections. I'm showing here a typical subsection of a qubit or a subsection of a chip. Yeah, so here you see a blow up of this little region here that contains a qubit and a readout resonator coupled to it. And these many qubits are coupled to each other as well to apply multi-qubit gates. So the radiative lifetime of this qubit here strongly depends on its electromagnetic environment, this complex metallodielectric electromagnetic environment. So from the point of view of the design of these systems, it is important to understand the radiative decay rates of individual qubits. Now, in this context, I have to introduce a few sort of ideas there. In this context, and you can think of this problem in either circuit quantum electrodynamics or atomic cavity QED, it's the same. The typical question you're interested in is the dependence of the radiative losses of an atom, the decay rate of an atom, that couples to a continuum through a cavity. Yeah. So you have to imagine that light can leak out here, for instance. So as one sweeps the frequency omega j of the transition frequency of this atom through the resonances that characterize any cavity, how does the lifetime of this qubit change? How does the lifetime of the qubit change? So it became possible really recently relative to sort of the life of cavity QED to characterize this dependence really well because of the availability of high precision microwave heterodyne spectroscopy. Here's a figure from a paper in 2008 showing some data and the result of various modeling results. Yeah, so it's pretty dense plot. But what I want to point your attention to are the points are the data for T1 times of individual qubits with different frequencies omega j. Now, these were really the same structure, different qubits, many, many experiments. Nowadays, you can actually sweep a tunable qubit across, changing its frequency omega j, and see how the T1 time changes. And you see that it changes within an order of magnitude. Yeah, so it's a substantial change. But what was pointed out then was, and repeatedly observed and pointed out later, is that a quantum model, an accurate quantum model to compute this dependence, really gives rise to a divergent series. And this is not only for qubit decay rates, also for cavity-mediated interaction strength between two qubits. Same problem. Yeah. So to discuss that maybe more quantitatively, I've just introduced some standard theoretical setup in thinking to think about this problem that gives rise to this divergent series. Usually, this goes through a quantum master equation approach. There is a Hamiltonian that you write for the cavity qubit system. This is, in this case, a Jaynes-Cumming multimode Jaynes-Cumming model. You have a two-level system or a spin that couples to a discrete and infinite set of modes of the resonator through this exchange interaction. Yeah. But because this cavity here is leaky, there are capacitive mirrors here, and light always leaks out. You have to also introduce dissipation rates for the cavity, yeah, kappa n. So these kappa n's are essentially the width of these resonances omega n. Yeah. So by the way, there are many different levels of modeling here in terms of these quantum models, and it turns out now we understand that really these should be understood as effective quantum models, as I pointed out earlier, and therefore you will see various levels of descriptions of these systems that appear to be inconsistent to the untrained eye at the beginning.
Can I ask a question?
Yes.
Is this still at zero temperature?
Yes, I think for what we want to discuss here, you can consider that we are at zero temperature, theoretically speaking. Yeah. Is that good?
Yeah, thanks.
Okay. So here's like a little glimpse into how these divergences arise, and at least in a simple setting, this is an argument actually in the original paper. So the Purcell decay rate of the cavity, right? The qubit omega j, frequency omega j, can decay to continuum only through the cavity modes in this description. Yeah. So each of these resonances of the resonator represent a loss channel. And so you can sort of write a back of the envelope calculation for the Purcell decay rate as at least in some limit called the dispersive limit, as a sum over the coupling Gn for individual resonator modes. So this coupling strength of individual of qubits to individual resonator modes over the detuning of the qubit from that particular resonator mode square times the damping, the loss of that particular cavity mode, this width. Yeah. And then you have to sum over them. Yeah. So you can do this at various levels of approximations. You don't need to look at this in the dispersive limit, and any way you do it doesn't change the result. Yeah. And it turns out that this sum is a divergent, and a divergent in a pretty bad way. And the reason, if you sort of follow the arguments going into this, is really can be traced back to electric field, the electric field per photon for every resonator modes at frequency omega n, that this coupling Gn that you see here, because of this dependence, goes like, is proportional to square root of n. Yeah. So if you then, and this is proportional to n, and if you do the calculation, as in this paper also, the kappa n is dependence is known, was expressed to be proportional to n square, you will find that this is pretty badly divergent, not even logarithmically. Yeah. So this now, interestingly, a classical microwave engineer's expression for antenna loss actually does a far better job, shown in dashed lines here. Yeah, so these red dashed lines. And so it is this leaves you at a stage where you wonder how to make sense of this state of affairs. So one really needs a quantum theory that provides finite lifetimes, because it's important for design of these chips. And also, one would want that this theory explains why the classical antenna formula works. At least in the limits, it works well. Yeah. So this problem, you will notice, is really reminiscent of divergence series for the lamp shift, the radiative correction due to vacuum fluctuations to the atomic transition frequencies, and is generally considered to be a solved problem through perturbative renormalization theory. Now, just in case, just as in the case of lamp shift, an atomic transition, lamp shift to an atomic transition in vacuum, also a superconducting atom, right? It's like a piece of metal that is interrupted by a dielectric interface in a Josephson junction. When it's inserted into a microwave cavity, it will also display a shift in frequency, and this is the lamp shift, no different. But interestingly, the problem here is far more difficult because the transition is due to the collective tunneling of condensate of electrons across a thin insulating barrier. Yeah. So now you're dealing with that, and there's really no renormalization theory invented for it. Yeah. As we discussed now, but from applications point of view, quantum computing, this does not really present a problem because we have very accurate spectroscopic tools available. One just measures the transition frequency of this artificial atom and inserts that value into the quantum master equation model that you have. As we discussed, however, the radiative decay rate is also divergent, as well as other QED observables that depend on vacuum fluctuations. And that is rather critical because you would like to be able to very accurately compute those quantities that limit your T1 and T2. Now, so that is really has been a problem in the field, and in a 2017 paper, we have shown that these divergences originate from a formulation of QED that does not respect the gauge invariance of QED, and a manifestly gauge invariant and a non-perturbative formulation does provide divergence-free expressions, interestingly. Yeah. So I'm moving to part 2 here. I'm done with the challenges, some of the challenges in the field. Yeah. So I want to begin this part by stating the problem definition in the most general way, independent of the particular QED platform. Suppose I have a material system, a cavity and an atom, and I want to be able to describe the exact quantum dynamics of the degrees of freedom within a finite volume. Yeah, I will call this finite volume the surface of last scattering. In other words, I would like to only use for the computation of the dynamics, quantum dynamics of the degrees of freedom within this volume, I would like to only use information within this volume. And that turns out to be possible. Yeah. Just there's a caveat that not only the volume information is needed, but also the information on this right on the surface of this finite volume. So this is sort of the 1+1D version of this. It's the Heisenberg-Langevin program. It's limited within its scope of what it wants to describe, but it does address this important issue in a mathematically consistent way. So the way this program works is that we put this source of loss scattering around, and we implement exact electromagnetic boundary conditions within on this surface, and that means transparent boundary conditions. Yeah. From this, it turns out you can write operator Heisenberg equations of motion for relevant system degrees of freedom within this chip. Yeah. And so this takes the form of like that in highly abbreviated form. And the important thing here to maybe contrast to standard QED is that it turns out Heisenberg picture contains a fundamentally different, gives you fundamentally different capabilities than the Schrödinger picture. And this is why Heisenberg picture is important here. The key object in then solving these equations is the kernel of the Volterra operator that goes into this into the operator equations of motion for the chosen degrees of freedom. And so you can think of this as really the qubit, singling out the qubits here that you see. You can think of this as effective equations for these guys. And the kernel is essentially the electromagnetic Green's function of all the remaining degrees of freedom within the finite volume with proper boundary conditions. Yeah. And then the question becomes, how do you compute the Green's function in a way that helps you solve these operator equations of motion? And there, our solution is to use a singular function expansion of the kernel. And I'll come to what that means shortly. Finally, this provides you a description of this entire system in terms of complex valued poles, discrete and infinite in number. And these poles represent hybridized excitations. That's important. So it's non-perturbative in that sense. And on top of this, however, you cannot really solve these. You can write these equations of motion, but difficult to solve. And you can solve them in a controlled expansion in a perturbation theory in the nonlinearity. So this is also very important because it's actually not, this kind of description is not perturbative in the fine structure constant, in the coupling between light and matter, but it's a perturbation theory in the nonlinearity. And that turns out to be also very key, very critical. Finally, that we envision a set of model order reduction levels to be residing on top of this fundamental formulation, mainly because even if you were to be able to solve these exact equations, if you're confronted with a 50-qubit chip, even that information that you would get is useless. To be earnest here. And so how do we do model order reduction to focus on the quantities that we are interested in? And that goes through and tracing out of electromagnetic degrees of freedom exactly or irrelevant degrees of freedom. So that I will show you how that is done for all the degrees of freedom outside this chip that we are ignoring, outside the volume, finite volume. It can be done. And then you can obtain equations of motion for spatio-temporally. So the next level here that we think is important is that that you would like you should be really interested in coarse-grained fields, because that's what you measure. And so why try to model something at a level of precision higher than what we can measure? So this is a very interesting question, and it leads to effective quantum models that are derived from a very accurate coarse graining methodology. And again, that those are like wide open questions that are important here. Okay, so now some key technical aspects of HLQED for prototypical problem.
We have a question in the audience.
Yes, please.
Just on the previous slide, how do you define in the field degrees of freedom what is irrelevant in the EM field?
Irrelevant, one example is when you, for instance here, right? If you take normally, if you were to do this, think of this as a computational electromagnetic problem, there would be a degree of freedom outside in the spatial region. And there would be attached a infinite dimensional, in principle, Hilbert space to that degree of freedom. So, but you're not really interested in this degree of freedom. And turns out every information about degrees of freedom outside this volume can be described by a certain sort of noisy sources on the surface, describing vacuum in thermal equilibrium outside. That can be done. And so in that respect, you don't want to deal with what's the degree of freedom outside here. What we do is we trace it out. And that's what you do also in quantum master equation method. These degrees of freedom don't show up.
Inside your volume, you still have an infinite field, degrees of freedom for a given mode of the field, no?
Correct. But you can also say, well, I'm not really interested in the cavity, but I'm only interested in what my qubit is doing. And you can trace out those resonator degrees of freedom and find an equation of motion for only your atom. I will show an example. So here's some technical aspects of HL, Heisenberg-Langevin formulation of QED for the prototypical problem of a qubit coupled to a cavity that in turn is coupled to infinite transmission lines on left and right. So this starts really with the Lagrangian for the macroscopic order parameter of the superconducting condensate. Standardly, this is derived from first thinking about lumped element representation of this transmission line in terms of capacitors and inductors, and then going to continuum limit. The atomic element, the Josephson junction qubit here, is really appears as a zero-dimensional nonlinear oscillator with a cosine type nonlinearity, with a coupling to the resonator field locally, shown in the rightmost term. Yeah. So there's some important mathematical and conceptual details here that shall not concern us at the moment for this high-level discussion. The end result is of writing down this is really a 1D continuum field theory with inhomogeneous speed of light, of this part here, coupled to a zero-dimensional nonlinear oscillator through this interesting type of coupling. The critical feature is that the electromagnetic environment is described not in terms of electric and magnetic fields or a vector potential, but the so-called node flux field. These are our fundamental variables that we express the Lagrangian with. And that, in turn, as you see, a temporal integral of the voltage across each of these capacitive elements, if you want to think in the lumped element picture. And if you think of that, it is really the electric field integrated over a small spatial and temporal interval. This will be important later when I think of extending this idea. So this is very different from standard quantization. For those who come from field theory, this is really a variant of boundary Sine-Gordon model, but with a gauge invariant coupling term here. Yeah. So now a few words about, yeah, I think I'm running short of time, so I will probably skip the slide, but there are a number of technical steps usually as one ends up with the effective quantum model that goes through some standard things. I think that folks that would deal with these kinds of quantum impurity systems know well, so I'm not going to touch the standard formulation, but at this point, this classical Lagrangian for the order parameter equations of the superconducting material is quantized, and there are a number of approximations to end up in this quantum effective quantum master equation. So how to deal with this because this issue of divergences here, it turns out that none of these approximations is key underlies the divergence that I discussed. It's actually a problem that is committed very early on before even getting here, and that is related to breaking the gauge invariance of the Hamiltonian. And that is what leads to the divergences. So how to deal with that is within Heisenberg-Langevin approach. Well, what we do is we take that Hamiltonian that I've shown in the previous slide and write the equations of motion. Yeah. And this equation of motion are for the quantized qubit field, right? That's zero-dimensional. Phi j is the qubit field. And for the resonator field, phi hat. Yeah. So these are quantized fields now. These equations are now written in dimensionless form, so hence the switch from capital phi to little phi. So one recognizes the top equation as the qubit nonlinear oscillator, yeah, coupled to the resonator field here at the position of the qubit x0. And the second equation, bottom equation, simply the wave equation for the quantum resonator field. Yeah. And then in this, and the qubit acts like a source, right, as a dipole source, let's say, which is delta function like in this formulation. And note the appearance of the qubit's position in two places here. The qubit changes the local speed of light in here in a way that I don't explicitly show, but the speed of light depends on x0, where the qubit is. So this is like the index of refraction of the cavity, if in optics, that changes because qubit is simply there. The atom is simply there. And for the following discussion, only parameter that is going to be important here is this chi-s parameter, which is again dimensionless, which is measuring the strength of atom resonator coupling. So when I talk about light matter coupling, I'm going to be referring to this chi-s here. So these equations can be solved exactly in a finite volume, and finite volume, I mean, I'm referring to between these two capacitors. Yeah. When these sets of equations are linearized, these are nonlinear equations through the Green's function of the wave operator that shows up here, yeah, in the second line. Yeah. So the basic idea is to solve the wave equation for the operators, resonator operator field, with a classical Green's function, and then let the qubit learn about its environment through this Green's function, and this Green's function implements leaky boundary conditions or transparent boundary conditions at the interface. So that's how we exactly implement the boundary condition in this case. Now a few words about the Green's function. Again, I think I'm running out of time, but what the Green's function, you can compute in many ways, yeah. But our favorite approach is a singular function expansion that sort of gives us an expansion of the Green's function in terms of constant frequency modes, yeah. And they can be solved with a special boundary condition within a finite volume. And I'm showing here an example of one of the modes, higher order modes of a transmission line resonator for chi equals 0 in red and for chi not equal to 0 in the dashed line. So you see that the mere existence of the qubit changes substantially the cavity modes that enter this Green's function. Yeah, that's very important. So so what's the sort of full procedure? Well, you take these nonlinearities, sum phi, expand them to linear order first, and leaving out the nonlinear terms for a perturbation theory in nonlinearity. Then you solve the remaining linear equations exactly. Then you trace out all the outside degrees of freedom outside your volume of the waveguide. So this xj is now the qubit field where all the outside degrees of freedom are traced out. In fact, here we trace out also the resonator degrees of freedom. Yeah, and then you can write an exact equation for this operator, telling you the displacement of the qubit. And it turns out it is this general form of described by a set of poles. And you see that this qubit is not oscillating at one frequency, but also at infinitely many other frequencies. The caveat is that the coefficients here are operator value. Now you would say, well, if P is complex value, this operator decays, and that's no problem because these are traced out, many degrees of freedom are traced out, and this X acts on the Hilbert space of only the Josephson junction qubit. Yeah. So all the amplitudes and the operator valued amplitudes and the poles can be obtained from a characteristic function that can be related to the Green's function and its integrals in frequency. So I have to skip that. But at the end, there's a very nice the calculation really boils down, the full quantum calculation boils down to a classical calculation of an electromagnetic boundary value problem. And so this 1 over that characteristic function that gives us the poles of the system. Turns out it is can be rewritten in a metamorphic form that in terms of its zeros and its poles. And those zeros and poles give a very nice interpretation of what is going on in this quantum system that I'd like to touch on just a bit. My clock is a little behind. I wonder how much time I have.
Well, you have 10 more minutes.
10 more minutes. Good, perfect. Yeah. So you see, I'm plotting here the poles of this linearized resonator qubit system. This is the qubit-like pole, Zj, when the coupling is 0. Yeah, so the qubit is not coupled to the resonator, chi equals 0. And here you see the poles of the resonator field. Because it's an open resonator, they are almost equally spaced, right? Because it's a Fabry-Perot type cavity. But they have imaginary parts that their decay rate becomes larger. Yeah, and so the qubit is raw bare frequency is detuned, is a little bit detuned from the first cavity mode, but it's also just right between the first and second cavity mode in this case. Yeah. So it turns out these poles of the uncoupled system, chi equals 0, are the zeros of this 1 over the characteristic function. Whereas the poles here, they tell us the poles, the modes of the coupled system. And so you see, when you turn on the coupling, what happens is all these poles move slightly. Yeah. And to understand the qubit decay rate, the T1 time, radiative T1 time that I've been discussing, and stating that it is divergent in a perturbative treatment, is then merely sort of refers to the shifts here, because qubit starts out as not dissipative because it's not coupled to anything. Yeah, so its imaginary part is 0 in 0 coupling, but when you turn on the coupling, it moves here, and so it acquires. There's a small frequency shift, and that's exactly the lamp shift. Whereas the shift in the frequency is the Purcell decay rate. Yeah. So you see the resonator poles also shift, right? And they generally acquire, they become less lossy as a result of the hybridization with the qubit mode. And that's because qubit mode is not lossy. So when they hybridize with the qubit mode, the loss of these cavity modes decreases. Yeah. So these are no more qubit and cavity modes, by the way. These are really hybridized modes that cannot be separated into light and matter parts. So then you can ask, well, if this is the Purcell decay rate when my bare qubit frequency was here, what is it when I sweep the frequency as we discussed at the very beginning in the experiments? How does the T1 time change? Well, it's here. You just have to trace the pole of the qubit-like mode, and you see that at points, particular points, where it hits resonances of the cavity, the T1 time becomes very small, well, because it becomes lossy and talks to outside through those channels, and so on, second mode, third mode, and so on. So in blue and red, I'm plotting actually the resonator modes, and you can trace their sort of loss rate. I call this also T1 here as well. And you see that they change slightly when they hybridize with the qubit. Okay, so now the nonlinearity is that that we sort of postponed later to address later is really the quantum mechanical part. Really, the quantum nature is in the nonlinearity, so that's important and that's critical in quantum computing. So what we do is then we just add this additional nonlinearity to the equations of motion. But now, now you want to make do a perturbation theory in this nonlinearity. But the problem is, it's very difficult, as we learned when we looked at this problem early on, to do perturbation theory in Heisenberg picture. And there's very little work about this. The problem is that these kinds of nonlinear terms, if you try to do perturbation theory, give in the long time limit divergent sort of secular terms, which is known in classical oscillator systems. So therefore, we had to come up with a quantum perturbation theory, a field perturbation theory, and generalize, extend what is known as multiple timescale perturbation theory and theory of classical oscillator systems, took the quantum domain. This is beautiful work by Bender and Betancourt, which took a first stab at it in 90s. So we have extended, we had to extend this to this kind of QED field theory to be able to do perturbation theory. And then what you get is interesting, that you get these lamp shift in correction to the lamp shift on top of what you obtain linearly due to the nonlinearity. And the lamp shift becomes an operator valued function. And that's not surprising, because this perturbation theory is on top of a harmonic oscillator with equal levels. And when you add the nonlinearity, all the levels shift differently. So all the transitions have a different lamp shift, and that's embodied in this operator. Anyway, so I have to sort of go to the final part of the talk. But it turns out you can use this ab initio model then to parameterize effective models. And if you do it right, it turns out that you can compute the losses without any divergences as well within the effective model. But it turns out then you find that the light matter coupling constants do not go as square root n for large n, but actually decrease as 1 over square root n for large n, which is very interesting and has been observed experimentally as well. So just a very few words about 3D modeling, because this is really limited in that we can describe one-dimensional transmission line-based systems, and one wonders how many of these ideas is really generalizable to three-dimensional systems. And the real quantum computing chips in these quantum computers are really three-dimensional systems. These chips, they have 3D boxes around them and so on. So it's a real challenge to do QED modeling of these systems. So this is very recent work, so I'm going to be very brief in it. What we want to do is now you want to model the superconductor as well. And that's, for that, you write the ordered parameter equations for the superconductor everywhere, wherever it is. And then the light part is simply the Maxwell's equation. And you reformulate then these two equations using hybridized gauge invariant fields, which contain part light, vector field, part the phase of the ordered parameter, right? So shown here. Now that turns out to be critical, that you use these gauge invariant hybridized fields. And this field A prime is indeed gauge invariant by construction. So then you construct, using this gauge invariant vector field, you construct a meshing of the 3D geometry where you introduce spatial integrals of them defined on edges. And this, it turns out to be very important. I won't be able to get into why, but what you have to do is you have to use a formulation of sort of finite elements in what's called discrete exterior calculus, so that the fields that you are computing are really coarse-grained fields. They are fields that are live on edges in your domain, and you do not care about what happens, at a smaller scale. And then you can write equations of motion for these variables very compactly in this discrete differential forms. And this works. We have a code to do that. There are, we check the basics of a Josephson junction in a three-dimensional superconducting cavity. You see that the excitations enter the superconducting sort of metal, penetrate it, and so on. But now you have these edge fields. You don't talk about electric and magnetic fields, but in terms of these sort of discretized edge fields. So that works. you can also it reproduces basic phenomenology like flux quantization, Meissner effect, and so on. So all this is pretty good as a starting point, but there are large, very interesting problems still remaining. I want to end this talk with the following observation. So QED is the most precise physical theory we have. And we generally think of it as complete after renormalization theory was invented. Number of really excellent scientists have contributed to the formation of this formidable edifice. But in view of more recent developments in QED, with solid state materials in particular, I think I tried to make the case to make progress, real progress, also in a way that it's applicable and you can build computational tools. It appears that one has to think of QED from a substantially different angle and introduce new theoretical and computational techniques. Yeah, and so I'm just popping up here a number of other platforms other than superconducting, and a list of sort of features that are needed for computational tools in this area with broad implications, not only for QED, but also for other gauge theories like quantum chromodynamics. Right, that brings me to really the final slide of people who have contributed to this talk. Now it's really the turn of this younger generation of students and postdocs to take on this journey. Thank you.